So as you should have got the announcement, I posted the solution to mission 4. So if there are any questions about that, feel free to ask. Any questions? All right, well, this brings us to chapter 4. And again, this material is on after test 3. So chapter 4 is the final chapter we cover, I think, as far as I remember. So this is on exponential and logarithmic functions. All right. So I should start out by giving you the definition, all right? And so here's the definition. If 0 is less than, well, let's say if a is greater than 0 and a is not equal to 1, then f of x equals a to the x for x in the reals defines the exponential function with base a. Now, I would first point out, like, this is a little bit surprising that you can calculate that sort of thing. I mean, well, let me break this down further. If we asked what does it mean when you write a to the x? Well, if x is like a rational number, we can make sense of that. You know what I mean? So I would just point out, if x is equal to like p over q, you know, which is a rational number, all right, then a to the x is equal to a to the p over q, and what we understand that to mean is the qth root of a to the power p, you know? So like, okay, that's just a natural extension of things we've already done, right? Like I could you know, pick a specific value for a and just start like tabulating values, you know? It wouldn't be a big deal. So, for example, I could pick base 2, right? A equals to 2, and I can make a quick table of values, x, and 2 to the power x, right? So if I put in, like, you know, minus 3, I'd have 2 to the minus 3, which is what? 1 over 2 cubed, right? That's 1/8. So in terms of decimals, that's what? 0.125, right? Yeah. And if I put in like minus 1, or well, say minus 2, I have 2 to the minus 2, which is 1 over 2 squared, right? Which is 1/4, which is 0.25, right? We could put in, say, 0. We have 2 to the 0 is what? That's 1, all right? And then we can look at things like x equals to 1. Well, that gives us 2 to the 1, which is 2, right? Or x equals to, 1.5. What would that mean? What's 2 to the 1.5? That would be 2 to the 3/2, right? So that would be the square root of 8, or of 2 cubed, right? Now what's the square root of 8? It's very close to the square root of 9, right? So that's approximately 2.9-ish, something like that. But my point is if you have any kind of rational value, you could understand 2 to that value in terms of, you know, a calculation with a root and a power, right? But you notice that this definition, it does more than that, right? Like x can be any real number. So we're also supposing that stuff like pi makes sense. Like I could calculate 2 to the pi. What would that mean? What does 2 to the 3.141 dot 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 mean? I mean, I can no longer say that that's, you know, some power and then take the qth root of that power anymore, right? Because pi is not a rational number. So what do we mean by 2 to the pi? Well, one way you could understand it is something like it's approximately equal to the, you know, what is pi? And what, can you tell me what pi is as a rational number? Well, you can't, but what's it approximately equal to? Like, you can calculate, by the way, 22 divided by 7 is like a pretty popular approximation for pi, because if you calculate 22 over 7, you get 3.14 and then stuff, all right? So 22 over 7 is matching pi pretty well, at least for the first 3 digits, yeah? So that we could calculate. That would be, you know, the 7th root of 2 to the 22. So I'll stop belaboring this point, but well, all I'm trying to tell you is, like, there is something to be asked and understood there. What do we even mean by 2 to an irrational power, right? To really understand that, you need to study calculus and start to think about limiting processes and things like that. But that said, we don't need to do all that because we have calculators, right? And so if I wanted to calculate 2 to the pi, what could I do? I could get out my handy-dandy calculator and try to figure out how to do 2 to the pi, right? So on this one, I think I would just hit the number 2 and then look for the exponent. So I do 2 to the pi. And when I do that, 2 to the pi, according to my calculator, 2 to the pi is equal to 8.8249777827. I mean, that's as many digits as my calculator gives 2 to the pi. So, and I think that makes sense, right? 2 to the 3 is 8. 2 to the pi is a little bit bigger than 8, right? Because 3.14 is larger than 3. Okay, anyway, just wanted to just take a minute here to try to appreciate the formula. I think it's worth noting that there really are, you know, we talk about power functions. What's a power function? What's that? Function with power? That's probably true. X to the n is typically the notation for the power function, right? What's the difference between the power function and the exponential function? Here, we typically fix n, and we let, you know, the base x vary, right? For the exponential function, what do? We fix the base a, and we let the exponent x vary. So the label of the function corresponds to the variability of the function. For the power function, well, that's not quite accurate, is it, either? I mean, we should call this a base function. We should call if we're going to call that an exponential function, we ought to call this a base function. We don't do that, do we? Oh, well. So the terminology isn't quite consistent. But really, if you start thinking about it, this g of x and that f of x, they're really just two sides of the same. I mean, it's really the same formula. We're just fixing or varying different aspects of it, right? Although typically with the power function, we do insist on n being like a natural number, right? But you could, in fact, talk about x to the pi power. That would be meaningful, all right? X to the pi power somewhere between, you know, like x squared and x cubed. Did we graph x to the pi? We did not, right? We just looked at x squared, x cubed, and then rational functions. Okay, so let's talk about different cases. So let's say observation. If we have f of x equal to a to the x, then what's f of minus x equal to? A to the minus x, right? Can you rewrite that? What's that? That's also equal to 1 over what? Yeah, 1 over a to the x, but the x becomes positive because we moved it downstairs, right? And we get, by another law of exponents, write this as 1 over a to the x. So what this suggests is that the graph y equals a to the x and the graph y equals 1 over a to the x are related how? By reflection over the y-axis. So just to, to keep it concrete here for a second, let's just look at 2 to the x. What's 2 to the x look like? Say again? Oh yeah, we could plot those points, right? Yeah, okay, let's do that. So at minus 3, we're about 0.125. Let's see here. So forgot to put my y-axis on here. Here's 1, 2, 3, 4, 5, 6, 7, 8. Right. So okay, great. Where's the y-intercept for 2 to the x? Yeah. Put it. Yeah. It's at 1, right? So 0, 1. There's the y-intercept. And when we get to 1, we're at 2, right? 2 to the 1. When we're at minus 1, we're actually at a half. We're at minus 2, we're at a quarter. When we're at minus 3, we're at an eighth. And I start to not be able to kind of, oh man, I can't erase that. I can't hardly distinguish. I mean, my ability to resolve 1/8 versus 1/16, it's not really very good. So anyway, it's something like this, right? What happens at 2? At 2, we're all the way up to 2 to the 2 is 4, right? And at 3, we're all the way up here to 8. So this is the graph. Y equals 2 to the x. And what I say in the black right above is that if you want to graph y equals 1/2 to the x, it's this picture just flipped over the y-axis, right? So y equals 1/2 to the x. Same song and dance, but we get small over here, and we get large over here. Now, I'm never very good at drawing these on the board. If the projector's working, I'll get it out. I'm not sure if it's been fixed or not. It was broken. Last week. We'll find out. Well, there are signs of life. I think I heard somebody come in here and fix it while I was in my office the other day. Oh, it looks like it's going to be there. You put away your personal information before I project that. Oops. Oh, the camera's over here, so nothing could be seen anyway. Have you guys recovered from the quiz not being today yet? I know, Evan, you tried to get me to, write that quiz last night, because I forgot about it, and I read Heaven's email, I was like, wait a minute, I need to write a quiz for tomorrow, but then I forgot about it. You just wanted the solutions. Ah, Very good. Yes, making a study sheet, that would be wise. Okay, so check this out. If we look at y equals a to the power x, I'll add a slider, and so this I'll just spend a couple minutes here looking at different cases because I think it's helpful to look at the projector here. It does a better job than I can. I'm not trying to get you to take a nap, if you're wondering. Let's see here. Although I would understand. It's kind of hot in here. All right. So this is y equals 1 to the x, right? Do you see why we want to rule that out in the definition? Yeah, this one's weird. It's not like the others. Things that I can say categorically for the others, I can't say for this. So we rule that out. And let me reset the... well, just for curiosity, see what happens when you look at negative values for a? Look at that. See that mess? See these things? So if you take the base to be negative, you can sometimes get real values, but sometimes not. And so like there's all kinds of complex stuff that's going on here. And I literally mean like complex in the sense of a plus ib. So if you want to understand negative bases, you really have to look at complex analysis. That is not this class. So we force the base to be what? Positive, right? So I'll say, I'm going to look at 0 to 4. And the step is the step size. I always put like 200 here and then I regret it. But what we should do is like put 0.01. Because I want to look at step size, 0.01. Something like that. All right, so look here. So you guys, you see what's happening? You see the graph? What does it look like? Yeah, it looks like a hill, but it's big when x is negative, right? And it's small when x is positive, right? So right now what I'm looking at, this is y equals 1/2 to the x, right? Now if you wanted to, I could add y equals 2 to the x just as a reference. See that? There's y equals 2 to the x. So you see that there's like that perfect mirroring between these two. Now what happens is I take the base and make it bigger. See that it gets, it gets less steep, right? Let's see here, until I get to 1, which will go back to that constant function, which is technically not an exponential according to us. And then once I get to bases larger than 1, it looks like this again. See that? So here's the story. If the base is larger than 1, then as x goes to infinity, the exponential blows up. However, if the base is smaller than 1, then as x goes to infinity, the function goes to 0. All right? In all cases, there's a horizontal asymptote for these functions, but not in both directions, right? When we looked at rational functions, we had horizontal asymptotes in the plus and minus infinity direction, right? Usually it was either 0 or 1 for us in the examples we looked at. But now there's an asymmetry, right? There's one direction we've got a horizontal asymptote, and there's another direction where this exponential function's blowing up. It's either going to blow up for the positive or for the negative, depending on whether the base is larger than 1 or less than 1. So that's pretty much it in terms of what this is what exponential functions look like, okay? Now, what I want to do here is look at, while I've got this out, let's look at the graph of a couple special ones. Let's look at, I've got 2 to the x up, right? Let's look at y equals 3 to the power x. All right, so you see what happens there? Now, let me zoom in a bit. Now, I happen to know that the tangent line to y equals 2 to the x is 1 plus what's called the natural log of 2. Oh, come on. Oh, I keep hitting B. What on earth? I can't see my keys. So this should give me a line which is, let's see if I can zoom in on this here. See this, guys? See that black line? See how it matches the green line like that? This black line is what's called a tangent line to the green line. And I'll put the tangent line to the purple line in as well. Turns out it's 1 plus, come on, I can't see the keys I'm hitting. So there's the tangent line to the, so again here, the 3 to the x is the purple, the 2 to the x is the green, the tangent line to the purple is the red line, the tangent line to the green is the black line. Now, these things, this number, natural log of 2 and natural log of 3, we'll explain more fully at the end of this chapter, but for our intents and purposes, what I want you to know is that the natural log of 2 is a number. It's about 0.693. All right. The natural log of 3 is a number. It's about 1.1. So what I'm telling you is that the tangent line to the 2 to the x function, it's a little bit shallower. It's got a slope of about 0.7, and the tangent line to the 3 to the x function is a little bit steeper. It's got a slope of about 1.1. So if you think about it, there must be some kind of exponential function between 2 to the x and 3 to the x, such that you got a tangent line which has slope what? You could find one that has slope 1, right? And so here's the thing. If I put in the tangent line with slope 1, which is what? 1 plus x, that's a line that has y-intercept 1 and slope 1, it's that blue curve. And we put what's called e to the x there. You'll see that e to the x is actually the tangent line to that one. Let me unselect these ones. Let me just leave on this one. Get rid of my tangent lines, except for the one that's interesting. So here, I'm going to zoom out a bit. The green line in the middle is what's called e to the x. It's between 3 to the x and 2 to the x. All right. So but the e to the x is the special function, which has a tangent line through the origin, with y-intercept 1 and a slope of 1. In other words, the exponential function is the function which has the value of the function is the same as the slope of the function at the origin. And it turns out that continues to be true at other points. The exponential function is the function which has the same value as it does slope at each point. But anyway, so I give this as just a quick explanation for what this number e is. And your textbook gives a rather different explanation for what it is, and probably the textbook's explanation is better for this class. I'm just telling you about how I think about it, typically in the calculus class. So, come on. All right, you can do it. Well, I was going to have to cancel class there for a second. Let's see here. I'll turn this thing off. So let's see here. Long story short, the definition, E is approximately 2.71 ... is the well, let's see here. What do we call this thing? bet they don't actually get well, the section title is the number E. This number E is typically referred to as the number E. So, well, it's the number E. But this is the base which defines f of x equals to e to the x. And I will usually refer to this as the exponential function, as in it's the most important one. So also we say base e. Now the definition your book gives is rather different. Your book defines e as being equal to the limit as n goes to infinity of 1 plus 1 over n to the n. But of course your book doesn't actually define limits, so this is just kind of a heuristic, right? Let's actually play with this formula for a minute and see if we can see how it gets us 2.71. Now this is built into your calculator, right? So like if you look at your calculator, you should find a built-in button for e. Like mine has e to the square. It's a built-in function. Okay, so let's try out the formula your book gives. So 1 plus 1 over n to the n, all right? And I'll put n over here. So how about 2? What do we got? 1 plus 1/2 squared, that's 1.5 squared. So that's 2.25. What happens when we look at n equals to 3? We get 1 plus 1/3 cubed, which is what? 1.333 cubed, which is going to give me what? .3, wow, already 2.37. I don't know why I'm excited about that. E is approximately 2.71. We're not even close to it yet. Let me jump ahead here. How about 10? What's 1 plus 1/10 to the 10th power? So 1.1 raised to the 10th power, what do we get? According to my calculator, 2.594. All right, great. We're still not there. How about to the 100 power? So 1 plus 1 over 100 to the 100 power. What's that give us? In other words, 1.01 raised to the 100 power. According to my calculator, if we can trust it. What's that? I get 2.705. If we take 1,000, so 1 plus 1 over 1,000 raised to the 1,000 power, 1.001 raised to the 1,000. If we trust my calculator, and I do, and as far as I know, it has no reason to plot against me. You know, we haven't reached the robot holocaust or anything like that. And even if we did, this has not got any kind of wireless connection. I think we can safely trust it. 2.7169 and stuff. All right. Now, if I just do e to the 1 on my calculator, what does that tell me? What is e to the 1? According to this calculator, e to the 1 is 2.71828 stuff. So goodness gracious, this is, it's taken its time to get to, to converge to the actual value. I mean, you have to go all the way out. Man, you have to go all the way out to 1,000 in this formula, even to get the first 3 digits of the exponential. So it's taking its time to actually converge to the number which it describes. But there it is. This is the exponential e. This is named in honor of a mathematician whose name is Euler. So, I know you probably want to say Euler or something, but that's Euler is how it's pronounced. And Euler did many things. Pretty much everything we cover in this course was first really done nicely by Euler. That's probably not an exaggeration. When did he do it? Let's see here. I want to say 1700s, basically. Like 1730 to 1770, most of this stuff. So, all right. Now, so there is a connection between this kind of calculation I'm doing right here and in a financial math. All right, and the connection is this. Have you guys ever heard of, you have a loan or compound interest or anything like this? Anyone studied how to get a loan and how interest is accrued? Do you know? Now, some people say yes. Some people say, I just take the loan out. I don't know how to pay it back yet. It will happen eventually, right? Okay, so, but some people said yes. All right, so. So here's the formula. It's called compound interest. So this formula, in some sense, motivates why we're interested in exponential functions. I mean, it's not the only reason. Exponential functions are interesting because they come up in like all kinds of science. Exponential functions are what you need to describe like growth of bacteria in a petri dish. Anytime you're looking at like population growth, which is unfettered, which is just sort of growing without, ignoring any constraints on the population growth, if it's just kind of growing freely, and exponential growth describes it pretty well. Radioactive decay is exponential decay. I mean, exponential formulas are everywhere in science, but also finances. So that's where they start with, because the financial application is like most close to this formula over here is basically the reason that they're interested in it. So the amount at time t is the principal, P, times 1 plus the yearly rate divided by the number of compounding periods per year raised to the number of compounding periods times the time in year. So R is equal to interest rate in per year. N equals number of compounding periods per year, and T is time in years. All right. Now, so this is the compound interest formula. Like here, for example, suppose we invest, let's say $10,000. All right, at a yearly interest rate of, what do you guys want to make it? You pick the interest rate. 5%? All right. So we'll write that as 0.05 for this formula. All right. And let's let the number of compounding periods be 12. So suppose it's compounded monthly, all right? Then what? Then after 6 months, how much do we have? So can you guys tell me what would I calculate here for this one? Like what's my t? So we want to calculate what's a of, so t is in years, right? So how many years is 6 months? What's that? A half, right? So t of 0.5 is what we're interested in, right? And so we've got 10,000 times what? Times 1 plus what was r? 0.05, right? We divide by 12, and we raise it to the nt power. So that's 12 times what? 0.5, right? And if that's the kind of investment that we have, if the bank is so foolish as to give us this deal, actually my kids have savings accounts which actually have 5% interest. It's very depressing. They've got like $300 or something in their account. They make more interest on theirs than we do on like tens of thousands of dollars over the course of the same time. It's very annoying. But 5% interest is kind of hard to come by these days. So if we plug that number in, what do we get? So what I would do is I would start by adding these numbers together, and then you got to look for your on my calculator there's like an x to a box function. This is something you need to figure out right before the final exam part 2. You need to learn how to use the functions on your calculator to actually calculate exponentials, right? Because these are things that we can't just, no amount of figuring is going to do this. I have to use a calculator. Anyway, so 1 plus 0.05 divided by 12. So this base, I get 1.0041. You got to be really careful. Like, I would recommend not. If you chop off digits in the base, you're going to get the wrong answer. So it's important to, like, when you're doing the calculator work, don't get rid of the extra stuff. Like, try to work with it and continue the steps. So I have this number. Now I want to raise it to the 12 times 0.5. That's 6, right? To the 6th power. And what I get is 1.02526 blah, blah, blah. So I multiply that by 10,000. What do I get? I get 10,252.61 61868, right? Dollars. And so what's the answer? How do we work with dollars? Like, what's the rule? We round to cents, right? So 62. So that would be the answer. We'd have $10,252.62. So it's not bad, right? If you had $10,000 sitting around and you could stick it in a bank with 5%, it would make you $250 in a half year, right? If it was compounded monthly, right? So what if it was compounded daily? What would that change? If it was compounded daily, then your n would be what, 365, right? So the calculation would change. What if it was compounded every hour, right? And if you keep continuing this idea and letting the compounding periods get shorter and shorter and shorter, this brings you to what's called continuous compounding. So continuous compounding, continuously compounded, is the limit as n goes to infinity of, the principal times 1 plus r over n raised to the nt power. And you can pull the p out, and by properties of limits and such, you can rewrite this as like, let's see here, how's it go? Well, you can let r over n equal to 1 over m. This is sneaky substitution your book does. So if this is the relation between n and m, then certainly if n goes to infinity, m also goes to infinity. So I can like trade my limit over n for my limit over m, and then this would be 1 plus 1 over m. And how do I write nt? Nt is what? Well, let's see here. Rm is equal to n in this substitution, right? So nt I could rewrite as m, and then all of that, raised to the RT power. And so the thing is, with that substitution, what you have in here is nothing more than the exponential. See, because we define the exponential to be the limit as n goes to infinity. I've erased it now, curses, but this piece right here goes to e. And so the formula we have is the principal times e to the RT, and that's continuous compounding. So a of t equals principal times e to the RT. This is continuous compounding. I can't spell. Continuous compounding. And we could compare. Should that be more or less than the monthly compounding, the problem we just did? If you're earning interest sort of like over smaller and smaller time intervals, you think about it, you should probably earn more, right? Because you're making money from the first instant that you put the money in the bank, and it just continuously compounds, right? So we could calculate that here. Just to compare to the one we did, a of 0.5 would be what? $10,000 times e to the what? RT, which is what? 0.05, and then t was what? 0.5, right? And what's that give us? It'll be pretty close to the number we already calculated. It won't be far off. E to the 0.05 times 0.5 times 10,000. I get $10,253 and 15 cents. So as you can see, the continuous compounding, hey, it's a little bit more than monthly, but if somebody sells you in this situation that, oh man, oh curses, I'm so sorry, people out of class. I'll blame heaven. Well, I mean, you're closest to the camera. It must be your fault, right? No, I forgot to pan after the video, unfortunately. Oh, so sorry, people out of class. I don't know. Anyway, so with the monthly compounding, we got 10,252.62 cents. With the continuous compounding, 253 and 15 cents, right? So if somebody says like, oh, I'll continuously compound your investment for just a $10 surcharge, you should be like, no, because it's not that much more. It's pretty, they're not far off, but that could add up after a while for a larger investment. Okay, and I think typically, a lot of financial institutions, they do go with continuous compounding because it's just easier, right? Like if somebody takes their money out of the bank in the middle of a month, then you can easily calculate how much money did their whatever accrue at that point, right? You don't have to wait and go, oh, well, the next compounding period is such and so forth a date, But the way actual loans work, it's more complicated, I suppose. You have these amortization tables and so forth. I won't try to get into that here. That's really not this course. So anyway. So for this reason, though, you can see that the exponential is interesting because it naturally arises from the study of compounding of interest, all right? Now, let us move along here. Now, there are functions related to exponential functions, which are just ever so slightly different. Just to give a summary here, what do we have? We have the y-intercept is 1, right? And so this would be like y equals a to the x, where a is greater than 1, right? That's what the graph looks like, right? On the other hand, if a is, between 0 and 1, then it looks like this, right? So here, y goes to 0 as x goes to infinity, right? On this side, y goes to 0 as x goes to minus infinity. So they both have horizontal asymptotes, but they're on opposite sides, right? But they have the same y-intercept, right? They all intercept at 1, y equals to 1, 0, 1 is the y-intercept, right, for all of these. And can you tell me more? Like, what's the range and what's the domain? What's the domain? So this is true for either case. For either case, the domain and the range is the same. What's the domain of a to the x? What's the range of a to the x? What are the allowed inputs? Remember what I said at the very start? I said for x and the reals, right? So the domain is just everything, all real numbers. What's the range? Zero to infinity, right? Now this is important because, well, I'll just get ahead of the story just a bit here. I'll ask you a question. Are these functions one-to-one? Like if you just focus on just the blue or just the magenta? It's unlabeled. This thing, whatever color this is. Are they one-to-one? Do they pass the horizontal line test? They do, right? So the exponential function has the one-to-one property. What does that mean? That means it has an inverse, right? And so the notation for the inverse function is actually, well, I'll tell you this. If f of x is equal to a to the x, then f inverse of x is denoted log base a of x. So the inverse function to the exponential is called the logarithm. In particular, log base a of x. All right? So like this log base a of x has the following. Log base a of a to the x is equal to x, and a to the log base a of y is equal to y. Right? And the top equation is for any real x. The bottom equation is for positive y. Right? Because what's the story? The domain of the function is the what? The range of the inverse function, right? And the range of the function is the domain of the inverse function. So I think that's worth talking about here before we get away from this. So we talk about this much more at the end of the chapter, all right? Like a whole section. We'll just talk about logarithms and their properties and so forth. But I just want to put it out here right now. It's nothing but the inverse function to the exponential, okay? And since we know graphs of exponentials now, we can already anticipate that you can only take the logarithm of something that's in the range of the exponential. Namely, we can only take the logarithm of a positive quantity, right? So now, so section 4.1 introduces exponential functions. It talks about their basic graphs like we already have, but then it does extra stuff. Like, could you graph, you know, y equals 2 to the x plus 1? What would that look like? Or could you graph y equals 2 to the x minus 1? So if you think about that, you should be able to take the basic graph that we already studied and shift up one to get this one, right? So like this should look like what? It should have, instead of being, it basically takes the 2 to the x function, just kind of pushes it up one, right? So basically this is, roughly speaking, a picture of it. How about, so this shifts, just shift y equals 2 to the x 1 vertically, right? If we wanted to graph y equals 2 to the x minus 1, what is that? That's a shift right, right? So shift horizontally, y equals 2 to the x 1 unit, right? So think about that as sort of my new y-axis. It's got a y-intercept of 1, and it does something like this. So just to give some name calling, if I call this f of x, and I call this one g of x, can you tell me the range of f and the range of g? What would the range of f of x be here? Is what? 1 to infinity. Yeah, 1 to infinity, exactly. So the range of f of x is 1 to infinity. What about the range of g? It's kind of a funny situation, right? If we shifted vertically, we changed the range, and the domain isn't changed at all, right? If we shifted horizontally, neither the range nor the domain is changed, you know? The range is still 0 to infinity, right? And the domain isn't changed either. So anyway. That's not unusual. Typically, you know, what happens horizontally versus what happens vertically for a graph of a function is distinct. So not too surprising. All right, let me see if I can erase this. All right, so moving along here. It brings us to section 4.3, which is the logarithm. And so here's the definition. So later in the chapter, we have more to say about exponential functions, like the last couple sections in the chapter, I think, look at, you know, exponential growth and decay and stuff like that. We'll look at that another day, I think. So definition. Mostly because in order to talk about exponential growth and decay, I need a little bit more about logarithms to do it nicely. And so if I try to talk about it right now, it'll just be kind of like awkward and not the best way, even though I think that's interesting and we should talk about it. Okay, so definition of logarithmic function, let a be positive number and a not equal to 1, then the logarithmic function with base a denoted log base a is defined by log base a of x equals to y if and only if a to the y is equal to x. So here's what he says in words. So log base a of x is the exponent to which the base a must be raised to give x. Also, another point of notation, if we write an equation in terms of exponentials, it's said to have exponential form. If we write the equation in terms of logarithms, it's said to be in logarithmic form. We'll talk more about that as we go on here, but let's see if we can calculate some of these things. So for example, can you tell me what log base 2 of 4 is equal to? Let's see here. So what we have is 2 to the something, fill in the blank here, is equal to 4. What do we have to fill in the box? 2, right? So log base 2 of 4 is 2. How about log base 2 of 1? Two to the what equals to 1? What do you have to put in that box to get a 1? 0, right? So log base 2 of 1 is 0. How about log base 2 of minus 2? So we just need 2 to the something equal to minus 2. It's a trap. Yeah, this cannot be done, right? You can't have 2 to some power equal to minus 2, right? This is not attainable with the exponential function, right? So this does not exist. Undefined. Now that's an important thing to be aware of because soon we'll be taking the logarithm of an equation, right? And if we're going to take the logarithm of an equation, we better make sure that we're taking the logarithm of something that's positive on both sides, right? Otherwise, when we take the logarithm, it's just nonsense. Okay, so how about this? Log base 2